Hello, and welcome to Calculus 1. In this video, we're going to talk about the most important idea in calculus, which is limits. Why are limits the most important idea in calculus? Because all of calculus is based upon this idea of a limit. In fact, the two most fundamental operations of calculus depend on the idea of a limit. The first is known as differentiation, where we calculate derivatives, and the second one is known as integration, where we evaluate integrals. Now, when we get to chapter 3, we'll introduce this idea of derivatives, and then later on, when we get to chapter 5, we'll begin talking about integrals. But for now, in this video, we're going to introduce this idea of a limit intuitively. And then later on, when we get to section 2.7, we'll come up with a more rigorous and formal definition of a limit. Okay, so to introduce this idea of a limit, we're first going to talk about average velocity, and that's going to lead us to this notion of instantaneous velocity. And then we'll see how they're related. So let's talk about average velocity first. Okay, so in this first example, they say a rock is launched vertically upward from the ground with a speed of 96 feet per second. Neglecting air resistance, a well-known formula from physics states that the position of the rock after t seconds is given by this function. S of t is equal to negative 16t squared plus 96t. The position S is measured in feet, with S equal to 0 corresponding to the ground, and we're supposed to find the average velocity of the rock between each pair of times given below. Okay, so for part A, let's find the average velocity of this rock between t equals 1 second and t equals 3 seconds. Okay, so first of all, this is called a position function. The reason it's called a position function is because it gives us the position of an object at any given time t. And S stands for the position, of course, and t stands for the time. And obviously t is being measured in seconds and S is being measured in feet. And we can represent the position function graphically, right, by calling this axis the t-axis and this axis the s-axis. And so if you graph this function, it looks like this. It's just a parabola that opens downward. And okay, so what we're going to do first is find the position of the object when t is equal to 3. That's its final position when t is equal to 3. And so we can do that by plugging 3 into this position function, because this gives us the position at any given time. So if you plug a 3 into this function, notice that, now you can do this on a calculator, but if you plug 3 into this function, you get 144. And so that's the position of this object, this rock, when t is equal to 3. It's 144 feet above the ground. Okay, and now we're going to compare that to its position when t is equal to 1. If you plug a 1 into this function, you get 80 out. Okay, so it's 80 feet above the ground when t is equal to 1. And so if we want to find the average velocity, we need to know how far it traveled over this time period. Okay, and so I think you can see it traveled 144 minus 80, it traveled 64 feet over a time period of 3 minus 1, which would be 2 seconds. Okay, so if you look at this, this is also a graph of that same function. And notice, again, this is 64 feet, right? 144 minus 80, and this is 2 seconds, 3 minus 1. And then when you divide 64 feet by 2 seconds, you're getting the average velocity over this time period. And so it's 34 feet per second. The other thing I want you to notice in this diagram is that you have two ordered pairs on this function, One of them is 3, 144, which is right there, and the other is 1, 80, which is right there. And if you draw a line between those 2 points and you find the slope of that line, the slope of that line would be rise over run, and in fact the rise is 64 and the run would be 2. And so the slope of this line is also 32, which just so happens to be the average velocity between these two time periods, or over this time period, right, between these two times. Okay, so that's an important idea. This is called a secant line. And the slope of a secant line happens to be the same as the average velocity in this case. Later on, we'll talk about a tangent line, and we'll explain the difference between a tangent line and a secant line. But for now, you should think of a secant line as going through 2 points on the graph of the position function, and the slope of the secant line is equivalent to the average velocity between the 2 points that go through that the line goes through. Okay, in this case, this point and this point. Okay, so let's go back and just work out part B. Now we want to find the average velocity between these two time periods. And so at 2 seconds, the position of the object is 128 feet above the ground. And then at 1 second, of course, it's still at 80 feet above the ground. And so if you want the average velocity, you would just take 48 feet and divide it by 1 second, and you'll get 48 feet per second, which is the slope of this secant line that goes through those two ordered pairs. Okay, on the graph of this function. Okay, so in terms of a formula, the secant line, which is the average velocity, right, those are the same, is s evaluated at t sub 1 minus s evaluated at t sub 0 divided by t sub 1 minus t sub 0. Okay, so notice up here, this is the position function being evaluated at two different time periods, labeled as t sub 1 and t sub 0. And then it's being divided by the length of that time period between t sub 1 and t sub 0. Okay, and so again, that gives you the slope of this secant line that goes through these 2 points, but it also gives you the average velocity between these 2 points in time. Okay, so in the next video, we'll talk about how we determine the instantaneous velocity of an object at a single moment in time, as opposed to average velocity, which is computed over 2 time periods. Okay, so we'll look at that in the next video. I hope you found this video helpful. Thank you for watching. Bye-bye.